As you see here, this is our computation domain. The computation domain consists of a large square inside which there are solids. The length of the solid, the cavity, is taken from the paper called as Zavo, in which they are specifying the length of the square as 0.0254 meters. Whereas the inside squares are given by the relation as you see here, which is denoted by A. Here N is the PPI. PPI means pores per inch. Here we are fixing the pores per inch as 5. This means that there will be 5 squares in the horizontal as well as in the vertical direction, which consists of total of 25 squares. And porosity of the eta symbol represents the porosity, where we can change the porosity from 0.5 to 0.9, but for this simulation we are sticking with 0.9, and applying these values to the formula given for A, we get the dimensions of the small squares inside the computation domain. Now we will try to create this geometry in a CAD software. By giving the various values for the squares, we can draw this geometry in Fusion 360. The values of the squares and the cavity has been calculated beforehand, and we are applying the dimensions readily. Here we are exporting the file as a step file so we can import it into Fluent. After creating the geometry in Fusion 360, we can now import the geometry into Fluent, and we can create the geometry inside Design Modeler. For importing the geometry, we just go to File and select Import File Geometry, External File Geometry, and select our exported geometry, and just click Generate. Then the geometry is generated in Fluent. After the geometry is created, we can now go for meshing. We'll click Select Mesh, and we try to insert inflation to the squares. We select the geometry and we select the boundaries. Here we are selecting the squares, individual squares. After we have selected the squares, we can now give the type of inflation we want. We are selecting first layer thickness method, and we are applying a first layer thickness of 0.3 mm, and we are generating it. Next, we will try to give an inflation on the boundaries of the squares. Here there are 4 edges. We select that. Now we give first layer thickness, and we give a height of 0.3 mm. Next, we give sizing to the squares. This will define the number of divisions on each edges of the squares. We change the type to number of divisions, and we give a number of divisions of 15, and we change the behavior to hard so that it keeps those values strictly. Next, we give sizings to the edges also. Here we also change the type to number of divisions, and we give it number of divisions of 200, and we also change the behavior of the method to hard. Next, we will give the method of generation of mesh. This will ensure that the type of cells in the mesh domain will be quadrilateral dominant. And we just click generate. The generator mesh looks fine for our purpose. As now the mesh is been generated, we can now go for naming the sides. Naming the sides allow us to apply boundary conditions to the flow domain. Here the top side of the square is named as top. Similarly, the left side of the square is named as left. The right side is named as right. The bottom of the square is named accordingly bottom. Now we select the individual edges of the squares to name them as blocks, and we name it as block. Now the cavity between the blocks is to be named as air, and we click update. Now the mesh is being updated to Fluent database. Now we can see the mesh has been updated, signified by the green tick mark. We can now go for solving our problem. We now open Fluent. Here we apply gravity, that is in the y direction, and it acts in the negative y direction, given by 9.81 meter per second square. Now in models we try to give energy because there will be heat transfer. Our fluid is air, but we are changing the properties of air for a mean temperature of 298 Kelvin, that means 25 degrees Celsius. We give the properties accordingly. Here we are assuming a bosonic approximation, so we are giving that condition here. All these values are got from thermal properties charts of air at a given temperature. For the boundary conditions, we are applying heat to the left boundary, and thereby we are maintaining a temperature of 303 Kelvin. And correspondingly, on the right side, we are giving a constant temperature of 293 Kelvin. So the temperature difference between the left and the right bar will be becoming 10. We are giving a convergent condition of 10 raised to minus 6 for the continuity x velocity and y velocity. This gives us a reasonably good result for ANSYS. We initialize the solution. We are applying hybrid initialization. Here we are patching the result, the field with a temperature of 298 Kelvin. That is the mean temperature. And now we can see the temperature is being patched over each node. You can see that there is 298 Kelvin everywhere. Now we can go for running simulation. Usually the conversions will happen in the range of 150 to 200 iterations, so I give it 300 iterations. We have completed our numerical simulation. Now we can go for post-processing our results. We are using CFD post for our final post processing. Here we are trying to change the appearance of the legend to our suitable needs. And changing the rotation of the text as well as the position of the legend. Now we can try to plot the contour of temperature. And creating the contour. Selecting the domain as symmetry one. I'm applying the results. Can you see the contour of the temperature? Here you can see that the left wall has more temperature when compared to the right wall. You can also see the stream contours for better understanding of the fluid flow inside the domain. The ultimate aim of our study is to find the Nusselt number of the domain, and the Nusselt number is given by the equation QL by delta T into K, where L is length, delta T is the temperature difference, and K is the thermal conductivity. Now we will show you how to calculate the Nusselt number inside CFD post. Here we are calculating the heat flux, which is given by Q in the formula. Here we select heat flux on the left side of the wall and we hit calculate. You can see the corresponding equation on how to get the heat flux. We copy that. Here in the expressions we create a new parameter, new expression called Nusselt number. Here we define the Nusselt number. This is given by Q into L. L is 0.024, which is the length of our domain, divided by temperature difference, which is 10, and the thermal conductivity of air at 298 Kelvin as 0.025925969. We calculate. Now we got the Nusselt number. The Nusselt number varies for different porosity. Here we are using a porosity of 0.9. Correspondingly, when we change the porosity from 0.9 to 0.7 to 0.8 to 0.5, the domain changes as well as the Nusselt number also changes.